Hello, I'm Christian Malaga, and this video will discuss a simple way to calculate the stiffness of structural systems. The key concept introduced in this short video is the calculation of an overall equivalent stiffness of a structure comprising members acting in series and in parallel. This basic concept will help you greatly in the structural analysis of simple and moderately complex structures and can also be of help when checking your calculations in everyday engineering practice. In the context of structural dynamics, we will often require the estimation of the stiffness of a structure in order to write down its equation of motion. In most common cases, we will be able to obtain a stiffness estimation directly, but in many others, we will need to apply any of the generic structural analysis methods available, like virtual work, flexibility, or stiffness methods. I claim that the stiffness of most systems of interest to structural engineers can be traced back to the stiffness of a simple cantilever structure. Take, for example, this vertical cantilever of height h subjected to a horizontal load F at its tip. This load causes a lateral deflection U at the top of the member. By means of the principle of virtual work, we know that the lateral deformation U can be estimated as the summation of these two integrals. First, the integral from 0 to h of the product of f and x squared divided by ei, where x is the vertical coordinate, e is the elastic modulus of the material, and I the second moment of area of the cross-section of the cantilever. This first integral is to be added to the second integral from 0 to h of f divided by the shear modulus of the material g and the cross-sectional area of the member, A. The first integral represents the flexural deformation, while the second one denotes the shear deformation. Note that we are neglecting any actual deformation here, but these can be added without any problem within the same analytical framework. Carrying out the integration, we arrive to this expression for the lateral displacement of the cantilever. And if we consider only the flexural stiffness contribution, the displacement U will be F h cubed over 3 times EI. Finally, by invoking Hooke's law, the flexural stiffness of the cantilever is found to be 3EI over h cubed. And that's all you will need to remember in most practical cases. Once you recall the expression for the stiffness of a cantilever, you can derive the stiffness of pretty much any other structural system by idealizing it as a combination of cantilevers in series or in parallel. The key is to understand the difference between the two combination rules. In a system in series like the one presented in this figure, the same force will act on springs 1 and 2, and therefore the total force F will be equal to the force in spring 1, F1, as well as to the force in spring 2, F2. On the other hand, the total displacement delta will be the sum of the elongation of spring 1, delta 1, plus the elongation of spring 2, delta 2. Looking at each spring individually, the force in spring 1 will be the stiffness of spring 1 times its elongation. From this, we can isolate delta 1 as F1 over K1. Similarly, for spring 2, F2 will be equal to K2 times delta 2. And isolating delta 2 will lead to F2 over K2. If we now substitute these two into the above expression, we have delta equals F1 over K1 plus F2 over K2. And realizing that F1 and F2 are both equal to F, the total displacement delta can become F times 1 over K1 plus 1 over K2. Then rearranging for F, we have the inverse of 1 over K1 plus 1 over K2 times delta. And hence, springs 1 and 2 can be substituted by an equivalent spring whose stiffness is the inverse of the sum of the inverse of the stiffnesses of each individual spring, or what is the same, the inverse of K2 plus K1 over K1 times K2. In the case of a system in parallel, both the springs 1 and 2 will necessarily elongate by the same amount, and therefore the total delta will be equal to delta 1, which will be also equal to delta 2. By the same token, the total force F will be the summation of the forces in spring 1, F1, and spring 2, F2. The force in spring 1 is equal to its stiffness times its elongation. Likewise, the force in spring 2 is K2 times delta 2. If we replace these into our previous expression, we have F equal K1 times delta 1 plus K2 times delta 2. Which is the same as K1 plus K2 multiplied by delta, since both springs experience the same elongation. Finally, the equivalent stiffness of two springs acting in parallel is found by adding their corresponding stiffnesses. With these principles in mind, and starting from the bending stiffness of a tip-loaded cantilever, can you estimate the sway stiffness of this 1-bay 1-story frame?